a plunger in a hypodermic needle is plunged at 25 millimeters per second. Determine the exit velocity V2 in millimeters per second. Here we have a rather large hypodermic needle. Its diameter is almost an inch. 25.4 millimeters would be 1 inch. This is almost 1 inch in diameter. And we have a plunger here forcing the fluid that's in this hypodermic needle out through this restriction and out the needle. This is traveling at a speed of 25 millimeters per second. And we'll assume that there's no loss of fluid backwards. This is completely sealed. So all of the fluid is being pushed forward, no leaks other than here coming out. And we are asked to determine what the velocity is here. Let's look at our equations that we want to use for this. This would be a classic example for the use of equation of continuity, this one here. And this basically states the fluid in must equal the fluid exiting. And here we already have a volume of fluid already within the hypodermic needle. And if we're going to plunge this forward, then all of this volume that we have here has to be exiting at this end here. So the volume flow rate in, even though it's already present here, has to equal the volume flow rate out. Something like this. Volume flow rate 1 must equal volume flow rate 2. And we'll call the beginning here 0.1. And at the end here, we'll call this 0.2. And we can expand these volume flow rate equations. Here they are here. Volume flow rate, A1, V1. So if Q1, V1, or Q1 is equal to V1, A1, and Q2 is equal to, well, using the same terminology there, V2, A2. Equating these two together, we have our equation of continuity, which is A1, V1 is equal to area 2, velocity of 2. This being the A1 and V1 here, 0.1. And this part, the exiting here, will be Q2 or V2, or the exit. Let's write down what is given. And looking at our equation, we need area 1, so we're given the diameter 1 right here. So D1 is equal to 25 millimeters. And the word problem is asking us to find the final velocity in millimeters per second. Hence, we're going to leave things in terms of millimeters. And instead of changing over to base units, we're going to follow the units. As long as the units work out, the solution here will be correct in terms of millimeters per second. So we have the diameter, but we need area, A1, and this is circular in shape. Every time you see the word diameter, you know we're talking about a circle. So if we were to look at it from that side, we see a circle, and that will be the diameter. And the area of a circle is pi r squared. Putting in the numbers, that would be pi times the diameter is 25. We need to divide that by 2 squared. That'll be the radius squared in millimeters squared. Putting this in our calculator, A1, going into the calculator without actually doing it, the answer is 490.87385 millimeters squared. Doing the same thing here at the exit. We need to calculate A2, the area, cross-sectional area here at 2. We're given the diameter 3 millimeters. And the area 2 is also pi r squared, the radius. And that would be pi times 3 divided by 2, all squared. So area 2 then is equal to, putting this in our calculator, and the answer is 0.06858 3 millimeters squared. We're also given the initial velocity right here. It is being plunged at a rate of 25 millimeters per second. So V1 here, the movement of the plunger forward, would also equate to the movement of the fluid going forward. So the velocity of the fluid is 25 millimeters per second. And we're asked to find what the exit velocity is here in terms of millimeters per second. We don't know. We have everything we need. Just a matter of putting these numbers into our equation and solving for V2. So doing that, we'll do that over here. Area 1, I'm going to use this term. There are other ways to solve this, mathematically that is, without having to do this in the calculator first, but we'll take this route. Millimeters squared times the velocity of 1 is given to us as 25 millimeters per second. And that's equal to A2, which is this term, 7.068583. And that is in millimeters squared times velocity 2. This little v right here represents velocity. Rearranging, dividing both sides by this value. You can do that over here. 490.87385 times 25 millimeters per second. Everything divided by 7.068 583 millimeters squared, and that is equal to velocity 2. Looking at the units, millimeters squared cancels out, leaving us millimeters per second, which is what we are seeking, in millimeters per second. Doing this in our calculator, the answer is 1736.111 millimeters per second. Considerably faster than the speed of the plunger. Now reducing this now here for the final answer to proper significant figures, we have two sig figs here, two sig figs throughout. Therefore, velocity of fluid at exit is approximately 1700 millimeters per second.